So, good evening, everyone.
Good evening, sir.
Oh, good. At least you can hear me. That's good. So, thank you for joining us for today's training on solving mathematics contest problems. So, we are about 5 minutes in, but we should be starting anytime now. So today's session will not be very long because we have only one set of 4 questions to go through. And we will be doing this every 2 weeks. So every 2 weeks we are doing this, and we hope to make it better and better as we go along. So in future, we want to also focus on some topics so that we cover some actual training on some given topics and example questions on the same topics. So this is going to be a regular thing for the rest of the year. Every 2 weeks, we shall be having these meetings. So I don't know whether we should give people another 2 or 3 minutes to join. Sometimes people have technology problems as they try to join. So if you can give them about 2 or 3 minutes, then we can start. I will share my slide. Then we can start going through the questions. You can see the numbers are growing. We're about 11. So I'll go ahead and start sharing the slide. And in about 2 minutes, we should proceed with the training. So I've shared my screen. Can someone confirm if you can see the screen?
Yes, you can see the screen.
Okay, that's great. Okay, so I'm going to put it on full screen mode, then we can start. So this training is supposed to support the CAPEC Kenya Mathematical Olympiad, which is an annual competition for high school students and has been running for since 2009, it's close to 11 years now, going to 12. So we just completed the second round of the 11th CAPEC Kenya Mathematical Olympiad, which started last year, but due to the pandemic, we got interrupted. We were not able to do the second round, so we just completed that a week ago. The results should be out this week, so we look forward to that. And the next edition would be starting in June, on the 10th of June. So to be able to help people understand or gain some more interest in this Olympiad mathematics, we will be running these trainings every 2 weeks, because one of the problems we had is there are teachers and students who say they had no exposure and no training to this. So this is supposed to help. This is also going to be useful for the clubs. If you have clubs in school, this can be very useful for the clubs to have material beyond the standard curriculum to discuss, something that is more challenging to the really good students who are in the clubs. So without much further ado, I will start on the problems, unless if there are any comments before. none. So feel free to, if you have a question in the process of the presentation, feel free to stop me and ask the question. That will be quite in order. And also the recording will be availed in the course of the week. I shall download it and make it available and share it as well. Maybe at the end of it all, I can put it on YouTube. I can share the link for the previous one. The one that we had last time, the link is on YouTube. I will share it immediately we finish the slides. Okay, so we will proceed to the first question. So, so the first question says that a rectangle has length p centimeters and width q centimeters, where p and q are integers. So if p and q satisfy pq plus q is equal to 13 plus q squared, calculate the maximum possible area of the rectangle. There's a typing error. It should be maximum possible area. 2 errors. The possible should be double S. But anyway, I think the point is clear. Now, the strategy we have taken here is to factorize, put all the unknown terms on one side and leave 13 on one end. Then we observe that once we have put all the unknown terms on one end, we can still factorize it further. Q is common, so it can be pulled out so that we have Q multiplied by P plus, it should be P plus 1, not P plus Q. I think there's an error there again. I will correct the slides before we share. So that should be P plus 1 minus Q. Okay. So, oh, I've skipped. So now we make the observation again that 13 is a prime number. So the only factors that 13 can have are 1 and 13 itself. So this means Q can either be 1 or it can be 13. And we consider each case in that order. When Q is 1, you can make substitute 1 for Q in this first equation, not the second, and the second one has a problem. There's a 1 that is supposed to replace the Q. So if you use this one, you'll get the wrong thing. If you substitute Q into the first equation, you will get that P is also equal to 13, because if Q is 1, all these things, 1 minus 1 will be 0, and P1 will just be P, so that P will also be 13. So that gives you one possible set of length and width for the rectangle. The second set is obtained when we take Q to be 13, and again, we go back with 13 in the initial equation, and we are able to compute P. Again, P is equal to 13. So those are the only two cases, and we are sure they're the only two cases because 13 is a prime number, and the only factors it can have are 1 or 13. So what this means is we pick the one with the largest length and width, and that is the second set, so that the maximum possible area will be 13 squared, which is 169. So this would be a square, actually. So that completes the problem. The answer is 169 square centimeters. So we will move on to the second question. This one may be a little more involving, but that makes it more interesting, I suppose. It says, let x and y be two positive integers such that x minus y is equal to 75. And the least common multiple of x and y is 360. So with that information, we need to find the value of x plus y. So we take advantage of the information that is in the already given in the question, and also what else? What other information can we bring along to help us solve the problem? So a few things we know. If you look at this equation, it says the GCD of x, y multiplied by the LCM of x and y will always be equal to the product of x and y. So with this in mind, if we keep this in mind, we need to work with the GCD at some point. LCM is already given. So we set the GCD to be D. And if the GCD of x and y is D, it means we can write x as a factor, as a multiple of D. We can also write y as a multiple of D. And x will be MD, y will be ND. And since D is the greatest common divisor, then M and N, the only common factor between M and N must be 1. If the common factor, if it's any number bigger than 1, then D will no longer be the greatest common divisor. So this must happen, that the GCD of M and N will be equal to 1. So also given in the question is that x minus y is equal to 75. And we can write this as MD minus ND, which is equal to M minus ND. We shall use this later. So we put this into this, put these values into this equation. We know the LCM is 360. We had labeled the GCD as D. And we know that this should be equal to XY. And X and Y are already written in terms of M here, and N, if you multiply them, you will get MN D squared. So if we divide both sides, the two extreme sides of this expression by D, we'll have 360 would be equal to MN D. So the fact that GCD of M and N is equal to 1 means that also the GCD of MN and M minus N will be equal to 1. I did not go into the details of why this is true, but if there's any, it can't be bigger than 1. Otherwise, then the GCD of M and N will not be equal to 1. That can be proved, but maybe I will not go into that because I've not included it in the. But if you have any questions about it and how it's obtained, I can explain it. So with this in mind, we can set up the next part. Since we know that the GCD of MN and M minus N was 1, if you multiply both of them by D, then the GCD of these two new numbers, MND and M minus N in brackets multiplied by D, must be equal to D. But we already know what these two numbers are. MND is 360, and M minus ND is just X minus Y, which was given as 75 in the problem. And the GCD of these two numbers is 15. So we now can confirm that the GCD of X and Y is actually 15. We had set it up earlier here. So D was supposed to be the GCD of X and Y. And now we have found the value to be 15 with the conditions given. So if we know 360 is equal to MND, we can show that MN is equal to 24. And M minus N multiplied by 15 is equal to 75, means M minus N will be equal to 5. So we have a pair of simultaneous equations here that we can solve. And when we do that, we find M will be 8 and N will be equal to 3. So with that, we can now find the value of X plus Y, which is what we were supposed to find at the beginning. So that X is the same as MD and Y is the same as ND. So X plus Y will be MD plus ND, which can be split further into M plus N multiplied by D. And M plus N is 11 and D is 15. When we multiply them, we get 165. So the question wanted us to get the sum of X and Y, and that is what we have found. And it is equal to So I'll move on to the next question. Again, this one is a little more demanding than the first one, and has a lot of interesting ideas, which we shall see. Very basic ideas, but quite interesting. So determine the number of acute angle triangles having consecutive integer sides and the perimeter not more than 2021. So this is good because it takes into account the current year. So it reminds us which year we are in. Now, a few things from the, you can set up these sides of the triangle differently from what I have here, but let's work with what we have. So the smallest side, we call it n minus 1. The next smallest side would be n, and the largest side, the longest side of the rectangle, would be n plus 1. Remember, this is possible because you know that the sides are consecutive integers. So we can set them up exactly as they are. You can also set them up differently and probably end up with the same answer. I haven't tried setting up. You could start with n plus 1, and n plus 2 and see where that leads. Now, a few things we will note is that the perimeter is less than 2021. So the perimeter is simply the sum of the sides. And if we add up the sides, we end up with 3n, and all that should be less than or equal to 2021. And if we divide both sides by n, then we know that since n is an integer, it will have to be less than the largest integer, that is smaller than 2021 over 3. So, and that will be 673. So n must be less than or equal to, I think this was a mistake. It should be less than or equal to 673. So we also know the triangular inequality, the sum of the other two sides should be bigger than the sum of the third side. So we add the two smaller sides, and we know that that should be greater than n plus 1. And when we simplify this inequality, we end up with n is greater than 2. So we have a lower bound for n, and we also have an upper bound for n. So n must be bigger than 2, but it cannot be more than 673. We also have a restriction that our triangle must be an acute angle triangle. So if you want, for the triangle to be, again, this is an error. It's supposed to be an acute angle triangle. So for it to be an acute angle triangle, this must change. It has to be acute. I don't know what happened there. There's an error. For this to be an acute angle triangle, we must have the following relation. We must have that the sum of the squares of the two smaller sides should be greater than the square of the largest side. You can obtain this by studying the cosine theorem. So what you will have to, you'll assign one of the angles as the largest, and then you try to compute the opposite side using the cosine rule and rearrange the terms. When you rearrange the terms, you will have to consider the largest angle being between 0 and 90. That guarantees that you have an acute angle triangle. So if the largest angle is between 0 and 90, this inequality will hold. That n minus 1 squared plus n squared will be greater than n plus 1 squared. If necessary, I can write out the details for that and share later. But for the triangle to be an acute angle triangle, the sum of the squares of the two smaller sides must be greater than the square of the larger side. So we work this out, and it reduces to, there's a bit of work involved there to eventually end up with the inequality here, which says n minus 4 is greater than 0. So if you want this quantity to be greater than 0, the only way that can happen is if this n minus 4 is also greater than 0. And that can only happen if n is bigger than 5 or is at least 5. So this gives us a new lower bound for n, so that we can say 5 will be less than or equal to n and less than or equal to 673. So any value of n here will give us the kind of triangle we are looking for. So if we count all the values of n between 5 and 673, including both, we should find that there are 668 triangles in total, because any value of n in here will give us a new triangle.
I think 69.
You could test manually. 669. Yeah, it's possible I made an error, because you have to subtract 673 minus 5 plus 1. Is that correct?
Yes.
Yeah, so it should be 669. We'll correct that, I think. What is 660? Yeah, 13 minus 5 is, yes, it's 8. So that should be 669. 673 minus 5 plus 1 should be 669. Thank you for the correction. So here is the last question. The question says, what is the largest value of a non-zero constant m if a quadratic equation mx squared plus m minus 3x plus 1 has at least one positive root? So we want it to have at least one positive root, but we don't want it to have both positive roots, or I mean both negative. It can be one or both positive, but we don't want it to have any negative, both negative roots. So we set up a situation where we guarantee that at least one root will be positive. Now we are interested in the real roots, and therefore the only time we'll have real roots is if the discriminant is greater than or equal to 0. This reduces to, if you work this out, you'll end up with this expression down here, m minus 1, m minus 9, greater than or equal to 0. So there's some work in between here. You need to expand the brackets and simplify to end up with m minus 1, m minus 9 multiplied by m minus 9 is greater than or equal to 0. So if you think of this as a quadratic equation, the coefficient of x squared is positive. That means the graph will be facing upwards and will cut the x-axis at 1 and 9. So anything between 1 and 9 will be below the x-axis, but we're interested in the section of the graph that is above the x-axis, and that will be for values of m that are less than 1 and for values of m that are greater than or equal to 9. So now if both roots are negative, then the sum of the roots is given by this. Again, this is just using the formula for the sum of the roots of a quadratic equation, where the quadratic equation is up here. Sum of the roots will be m minus 3 over m negative. And this is supposed to be less than 0. So for this to be less than 0, it means this numerator must be positive. So if the numerator is positive, that can only happen if m is greater than 3. Is there a mic that is on? Or so we require that m must be bigger than 3. That's the only time we can guarantee that both roots, if both roots are negative, then m must be bigger than 3. Okay, and that is not what we want, but let's see how the product also, the product of the roots will also be 1 over m. Again, this is just using the property of the product of the roots of a quadratic equation. So 1 over m must be positive. That must be positive because if both roots are negative, then, I mean, if both roots are negative, then their product must be positive. So, so the only way we can guarantee that there's at least one positive root is if m is less than or equal to 3, because anything bigger than 3 guarantees that we have both negative roots. So this means that if you combine m less than or equal to 3 with the previous inequality that we had earlier, this one that says m is less than or equal to 1, our values then must be less than or equal to 1, right? And we're looking for the largest positive value. I think that's what the question asked. And if m is less than or equal to 1, then the largest possible value is therefore 1. So 1 is the largest possible value that guarantees that this quadratic equation has at least one positive root. So I think that's all for today. That's all the questions we had for today and the solutions. I will correct the errors on the slides before we share the slides, but the video will go out as it is, but the slides will be corrected. Now, so thank you for listening. And now if you have questions, you're welcome to ask questions. Are there any questions? So thank you very much for showing up. If there are no more questions, we can I think we can bring the meeting to an end. Any comments? So we also would need some feedback to see if you'll find if there's anything you'd want done during this meeting. Or we repeat the last question. Okay. I will repeat the last question again. Since we have a bit of time. So the last question is here. So the question asks, what is the largest value of a non-zero constant m if a quadratic equation mx squared plus m minus 3 in brackets x plus 1 has at least one positive root? So to answer this, we need to find values of m that will guarantee that there are no negative, that the roots are not both negative. So that becomes our strategy. Find out how do we eliminate the values of m which give us both roots being negative. And if we eliminate those, the remaining ones must give us the desired result. So first of all, for the equation to have real roots, we must have the discriminant being greater than or equal to 0. That is m minus 3 squared minus 4m will be greater than or equal to 0. So when you simplify this will be m minus 1 multiplied by m minus 9, which is greater than or equal to 0. Now, if you think of this as a quadratic equation, where the if the graph is facing upwards, then you'll have, if the discriminant is to be greater than or equal to 0, then m must be less than or equal to 1, or m must be greater than or equal to 9. And for any values between -1 and 9, the graph will be below the x-axis. So these are the values that will satisfy our inequality. Any value of m less than or equal to 1, or any value of m that is greater than or equal to 9. So we know the formula for the sum of the roots of a quadratic equation. And if this was ax squared plus bx plus c, the sum of the roots will be minus b over a, where b is m minus 3 and a is m. So this gives us minus m minus 3 over m. I want this to be less than 0. We already have a negative out here. And our m is, sorry, we already have a negative out here, and we need this quantity to be we need this quantity up here to be positive for this thing to be to continue to be fully negative. So this guarantees that m for that to happen, m must be greater than 3. So if m is greater than 3, then we are guaranteed that this quantity will be less than 0. So this gives us some lower bound for m, which guarantees that both roots are negative. So for anything bigger than 3, both the roots will be negative. If you start from 3, this quantity will not be negative. So it will be actually 0. So anything bigger than 3 will guarantee that both roots are negative. We also know that the product of the roots is given by 1 over m. And if both roots are negative, then 1 over m must be greater than 0. So for the equation to have at least one positive root, then we must violate this condition that requires that m should be bigger than 3. So if you want at least one root to be positive, then you must violate this condition, and that forces us to consider m is less than or equal to 3. But the values of m that we need to consider are less than 1 based on this inequality that we have here. So combining this, m is less than or equal to 1, and m is less than or equal to 3, we end up, the only one that will hold will be m less than or equal to 1. If they have to be true at the same time, then if m must be less than or equal to 1. So the largest value of m is 1 in this case. I hope that is clearer, or has made it a little clearer. So I think I'll stop sharing at that point. So thank you for attending. So if you have no more questions, you are free to leave. I need to discuss. I will ask Jared, if you don't mind, you can hang on. We have Andreas Holmstrom from Norway, and he has some ideas about mathematical training that he wanted to discuss with us. So We can ask the rest to leave. And thank you for showing up for this class. And we'll be back again in 2 weeks' time with another set of questions to solve.